Starship is continuously evolving, becoming bigger and more powerful over time. To create such giants, many aspects of its design and construction have changed, particularly the welding methods used in its assembly. With new versions on the horizon, including the highly anticipated V3, it's a great time to look back at the evolution of these welding techniques and explore what upgrades we might expect in the upcoming version. So how have these welding methods progressed, and how will they continue to evolve alongside Starship's development? Let's dive into this topic on today's episode of Great SpaceX. The massive Starship rocket, a symbol of SpaceX's vision for interplanetary travel, is not a monolithic structure but rather composed of meticulously assembled stainless steel rings. These rings are welded together into segments and then stacked using advanced welding techniques. While welding might seem like a straightforward process, its execution is anything but simple, requiring precise methods and careful attention to detail. Elon Musk has often highlighted the critical importance of welding in the construction of starships, stating, "A lot of ways to melt and join steel, mostly just needs to be welded consistently and with precise parts." This precision becomes even more vital when using stainless steel instead of the carbon fiber utilized in Falcon rockets. Stainless steel offers several advantages, including lower cost, greater durability, and versatility in shaping. However, it also presents challenges, particularly in its tendency to retain heat, which can complicate the welding process. In the early stages of Starship development, SpaceX employed the flux-cored arc welding method, FCAW. While functional, this approach had its limitations. Early Starship prototypes appeared rough and unsophisticated, with visible welding seams and traces. The high heat generated by FCAW caused the stainless steel to warp and deform, resulting in an uneven surface. Additionally, stainless steel is prone to scratching, making it impossible to grind down the weld marks for a smoother finish. These issues were not merely aesthetic, they posed real structural risks. Imperfect welds could lead to cracking during the rocket's operation, particularly during the intense stress of atmospheric re-entry. Such vulnerabilities could compromise the integrity of the weld and jeopardize missions. Recognizing these shortcomings, SpaceX transitioned to a more advanced welding method called TIG, tungsten inert gas welding, or TIG-tip semi-automatic welding. This technique provided significantly greater control over the welding process, resulting in cleaner, more uniform seams. Musk himself highlighted the benefits, explaining, "These parts are stamped versus manually bunked formed, and TIG-tip welded versus flux core. Higher precision, stronger joints, and 20% mass reduction." The advantages of TIG-tip welding extended beyond aesthetics. The method produced stronger welds, reducing operational risks and allowing for thinner stainless steel rings with fewer welds required. Starship's overall mass decreased by up to 20%, a critical improvement for a spacecraft designed to carry large payloads and traverse extreme environments. SpaceX didn't stop there. They continued to enhance their manufacturing processes by introducing laser welding machines. These automated systems significantly increased precision, further improving the strength and appearance of the Starship prototypes. This progression is especially evident when comparing the nose cones of early prototypes with those of more recent iterations. The newer prototypes boast a sleek, polished look, free of visible weld marks, while benefiting from faster and more efficient production cycles. Another crucial upgrade in Starship's evolution was the transition from 301 stainless steel to 304L stainless steel. This newer alloy offered improved corrosion resistance, a critical factor for both manufacturing and operation in space's harsh conditions. The enhanced composition of 304L made the welds up to 4 times stronger than before and increased the material's ductility by 25% at extreme temperatures. Additionally, its low carbon content helped to prevent cracking, further enhancing the rocket's reliability. These advancements represent a culmination of SpaceX's relentless pursuit of excellence. By refining their welding techniques and upgrading materials, SpaceX has transformed Starship into a spacecraft that is not only visually impressive but also exceptionally strong and durable. The combination of precise welding, advanced materials, and automation has paved the way for a rocket capable of withstanding the demands of deep space exploration. Starship's journey from rough early prototypes to its current state is a testament to SpaceX's innovative spirit. Each improvement in welding methods and materials brings humanity closer to realizing the dream of sustainable space travel. Through these advancements, SpaceX continues to set new standards in aerospace manufacturing, proving that no detail is too small when building the future of interplanetary exploration. SpaceX is now taking the technologies and lessons learned from earlier versions of Starship and applying them to its new iterations, pushing the limits of innovation even further. Currently, SpaceX is in the process of producing Starship V2, incorporating several design changes and laying the groundwork for the upcoming V3, a colossal version anticipated to reach a towering height of 150 meters. In these new versions, durability remains the top priority, as Starship aims to venture deeper into space rather than just reaching orbit like V1. It will face increasingly harsh conditions, and re-entry processes, in particular, will expose the ship to extreme temperatures, demanding robust design and materials. After 6 flights, Star V1 has demonstrated steady improvement, especially in handling the challenges of re-entry. However, full recovery remains elusive, highlighting the need for further advancements in production methods. Encouragingly, the early prototypes of V2 exhibit notable enhancements. A side-by-side comparison of the nose cones from V1 and V2 reveals a significant upgrade. The welds on V2 are practically invisible, giving the impression of a seamless single block. This not only suggests improved durability but also highlights advancements in welding technology. But durability is just one part of the equation. SpaceX is also focused on reusability, striving to ensure their rockets can perform multiple flights. Enhanced welding methods will play a crucial role in achieving this, as they reduce structural stress and streamline refurbishment processes. Another critical advantage of the new welding methods is speed. With significantly increased automation, production times have seen a dramatic boost. The first prototype of V2, Ship 33, was built in just 42 days, a testament to SpaceX's commitment to efficiency. However, the true effectiveness of the V2 welding techniques will be tested in actual flights, beginning with Flight 7 early next year. These flights will provide essential data for further refinements, paving the way for the development of V3. Once the welding and production principles stabilize, SpaceX's next step will be replication on a larger scale. That's where Star Factory comes in. It's already operational, producing parts continuously to meet the demands of mass production. Additional welding systems may be needed, alongside expanded facilities like the planned Giga Bay. This new assembly bay will be taller and wider, capable of accommodating the larger Starship versions down the pipeline. Regarding deployment schedules, SpaceX has ambitious plans for both Starbase and its Florida facilities, which are expected to utilize V3 versions. NASA has stated that Starship will move to Florida operations once it achieves a cadence of 1 launch per week, a milestone likely to occur early next year. To meet these goals, preparations for the production system, including welding technologies, are essential and must be addressed now. SpaceX's ultimate vision is to produce 1 Starship per day, necessitating round-the-clock operation. Continuous advancements in welding and overall production methods will be critical to achieving this target. Beyond production, SpaceX is enhancing its testing and launch systems to complement its manufacturing capabilities. The flame trench test system, already operational, has proven highly effective. This innovation allows SpaceX to increase its launch rate, with newer prototypes often ready before previous versions have even flown. Significant upgrades are underway at the launch site, including the addition of Launch Tower B and a new orbital launch mount. These systems are key to increasing Starship launch frequency and eventually catching the rocket. They are expected to be replicated as Starbase expands and new launch facilities like those in Florida are established. SpaceX is building an unprecedented system that integrates advanced production, rigorous testing, and cutting-edge launch capabilities. Every detail, no matter how small, supports the broader vision. One day, Starship will take humanity to the Moon and Mars, achieving what once seemed impossible. These milestones will rest on countless smaller innovations, such as improved welding techniques that strengthen its foundation. What do you think of SpaceX's Starship development, especially the evolution of its welding methods? Share your thoughts in the comments section down below, and don't forget to like and subscribe for updates on SpaceX's incredible journey. Wrapping up that whole segment with Starship, let's shift our focus to an exciting update on Viasat Space Industries and their recent milestone, a significant $48 million contract awarded by the U.S. Air Force Research Laboratory, otherwise known as AFRL. Viasat Space Industries is well recognized for its innovative work in developing and operating re-entry capsules designed to return specialized cargo from space. Earlier this year, in February, Viasat successfully completed its first mission, W1. This mission marked a groundbreaking achievement, the safe return of a capsule carrying pharmaceuticals created in a microgravity environment. The capsule re-entered Earth's atmosphere at a blistering 18,000 miles per hour, around 29,000 kilometers per hour, and executed a precise landing in the Utah desert using a parachute system. Building on this success, the AFRL contract underscores the increasing interest in commercial re-entry vehicles for cutting-edge military applications. This partnership specifically aims to test military payloads at hypersonic speeds, a notoriously complex challenge in aerospace engineering. Hypersonic testing involves navigating extreme thermal protection, maintaining accurate navigation, and ensuring reliable sensor performance, all critical components for the next generation of defense technology. The collaboration also offers a cost-effective solution for the U.S. Space Force, as it provides